Thermal physics and ideal gases. This is a kinetic theory. Here you need to know the spacing, ordering and motion of all solid, liquids and gases, here, and here. In the spacing of a first solid, the spacing is very, very close, as you can see here. It's regular ordered, like in a lattice, and the motion is oscillation about a fixed point, as you can see here. In a liquid, the molecules are still touching, still have some gaps, but they are still touching. The ordering is irregular, no real correlation, and the motion, they move past each other. In gas, the spacing is well spaced. The ordering is random, going all different directions, and then motion is random also. Brownian motion. This experiment shows the behaviour of air molecules. The air molecules themselves are too small to observe, however they do interact with larger gaseous molecules to exhibit their behaviour. Smoke particles are used for this demonstration, as shown here. From Brownian motion we observe that the smoke particles have continuous haphazard motion, which means particles are continuously moving at random velocities, no correlation, nothing whatsoever. From that we can conclude, this is what the mark schemes, what I wanted to hear. The air molecules are very small. Oxygen and nitrogen are much smaller than the wavelength of light, visible light, can't see them. Okay, fine. The air molecules are continuously moving. As I say, the smoke particles are continuously moving, therefore the air particles are continuously moving as well. The molecules of air have very high velocities. Since the smoke particles are much larger and have a higher mass, to be able to compensate for the overall momentum change for the smoke particles to move, they must have a very, very, very high velocity. As you can see, smoke particle here, very large, small one here. We have to move this, but that has to be going very, very high velocity, and they move fast. A commonly asked question is how a gas assesses a pressure. The definition for pressure is force exerted normally per unit area. A gas is made up of many atoms or molecules in random motion. Molecules collide with the walls of the container. This will create momentum change. Many collisions per unit time, rate of change of momentum, Newton's second law, is proportional to a force on the particles. By Newton's third law, an equal and opposite force is exerted onto the walls of the container. The force on the walls of the container divided by area is pressure. Melting ice at a constant rate. Here we talk about the internal energy. Internal energy definition is the sum of the random distribution of kinetic and potential energies associated with the molecules of a system. When solid, the kinetic energy and a small increase in potential energy occurs. When melting, all the potential energy is increasing. When liquid, up this gradient here, we have kinetic energy increasing and a small increase in potential energy also. When boiling, there's only an increase in potential energy. The reason for we only have an increase in potential energy at boiling and a melting point is because the kinetic energy remains the same, as there's no increase in temperature. Kinetic energy is equal to 3/2 kT. All the potential energy increases, and when a gas, on this gradient here, there's only an increase in kinetic energy. Evaporating. In a liquid, the atoms or molecules have random distribution of energy. Some molecules will have enough energy to leave the liquid. This is evaporating. The remaining atoms will have a lower average energy, so the temperature will drop. Melting. The average energy of the molecules is enough to break from the organised structure and move past each other. Boiling. Here the average energy of the atoms or molecules is equal to the energy needed to leave the liquid. The definition of latent heat vaporization is the energy required to change the material from liquid to gas at a constant temperature. The definition of latent heat of fusion is the energy required to change the material from solid to liquid at a constant temperature. Specific heat capacity. The definition is the energy required per unit mass of the substance to raise it by a unit temperature rise. An experiment to calculate specific heat capacity is used as an electrical experiment. The setup is shown here. We have a material. This can be liquid or solid. We have a circuit with a power supply, a electrical heater, and a thermometer to measure temperature. The measurements that need to be made are temperature, which is done by a thermometer, current of the electrical system, which is done by a ammeter, potential difference by a voltmeter, time by a stopwatch, mass of the material, weighing scale. The calculations that need to be done to be able to calculate a specific heat capacity is change the temperature done by the final temperature minus the initial temperature. The energy input is W is IVT, current times voltage times time, a G482 equation. Here's the rearrangements of the equation. E is equal to MC, sorry, there's supposed to be a delta theta there. E is equal to W, W is MC delta theta. IVT is equal to MC delta theta. IVT over M delta theta is equal to C. Inaccuracies. Mainly for this experiment, the inaccuracies is heat loss to the surroundings. This will make the delta theta or changing temperature smaller. Therefore, the specific heat capacity will be larger, too large in this case. To solve this, insulation is used to reduce the heat loss, and therefore making the changing temperature larger, which is what we want. The electrical heater will continue to heat the material after the power supply has been turned off. To solve this, you're going to wait until the material has reached its highest temperature and then use that to calculate the temperature change. This experiment reveals that the thermal energy will flow from a hotter to a cooler material. A body with a high temperature doesn't necessarily have more thermal energy than a cooler object, which is larger. For instance, if you've got say a small metal ball bearing, which is about 100 degrees C, and you have a large metal 1 kilogram piece of iron, which is 50 degrees C, the iron will have more thermal energy. Now you have to be able to transfer between Celsius and degrees. Going from Celsius to Kelvin is plus 273. So for example, 23 degrees C will go to 296 Kelvin. Kelvin to Celsius is minus 273. So if we've got 23 Kelvin, it goes to minus 259 degrees C.
Ideal gases. Boyle's law is a law we should be familiar with. It states the pressure exerted by a fixed mass of gas is inversely proportional to its volume, provided the temperature of the gas remains constant. From this, we can get the equation PV over T equals constant. This equation becomes very useful when a change occurs to one of the conditions in an ideal gas and one remains constant. We manipulate the fraction to find the third condition. There are 5 basic assumptions of the kinetic model of ideal gases. The first one, large number of molecules with rapid random velocities. The second one, the forces between the molecules are negligible except during collisions. The third one, the volumes of the molecules are negligible compared to the volume occupied by the gas. The fourth one, the time collision is negligible compared to the time between collisions. The fifth one, the collision of molecules with each other and with the container are perfectly elastic. To remember these 5 assumptions, you can use many different methods, such as the one Ned told us in class. These assumptions are necessary, and real gases may differ vastly. Moles are frequently used in the calculations about ideal gases. 1 mole of any substance contains 6.02 times 10 to the 23 particles. This is known as Avogadro's constant. We can incorporate the amount into the equation above, and we get the equations PV equals NKT and PV equals nRT. On the right hand side of the screen is a key which shows what all of the symbols mean and where you can find them, if you can find them on the datasheet, and their units. The Boltzmann constant, K, and the universal molar gas constant, R, are related to the Avogadro's constant by the equation K equals R over Na. The mean translational kinetic energy of an atom of an ideal gas is directly proportional to the thermodynamic temperature. This relationship is described through the following equation, E equals 3 over 2 kT. We also know that E equals half mv squared from G481 and 2. From these equations we can derive the relationship V is proportional to the square root of T. An example of how this is applicable to real-world situations, if we increase T by a factor of 4, the average velocity will increase by a factor of 2. A commonly asked type of example question. Estimate the mean speed of carbon dioxide molecules at 0 degrees Celsius. The molar mass of carbon dioxide is 44 grams. To start, we will list the equations we will use. E equals 3 over 2 kT and E equals a half mv squared. We know K from the datasheet, and we need to work out T. We have it in Celsius, but we need to turn it into Kelvin, so to convert we add 273 Kelvin. We also need the mass of a molecule. We have the mass of 1 mole of carbon dioxide molecules, and we know the number of moles. The number of moles, Avogadro's constant, and the mass, 44 grams. So to work out the mass of a single molecule, we divide the MR by Na, and we get 7.31 times 10 to the minus 26. If we rearrange our equations above to find V and substitute the numbers in, we come to an answer which is correct to 3 significant figures.